I am a beginner for this symplectic community, and therefore I'm working with Juan Rosas Quintero, who is working in robotics. And some slides to introduce the fact that I have some general culture about the principle of distinction, which is used in the huge variety of fields in science. And I have a background in numerical analysis and finite elements, and for me, the discovering of least action principle was acting very concretely in the finite element methods, and therefore I refer to Courant paper in 43. And for the natural idea is I've got this idea during my thesis. It was to switch from minimization of actions to dynamical systems. And a colleague said to me, "Oh, no interest. You have implicit schemes and so on." And there is. Comment est-ce qu'on fait pour pointer le truc là? Le point rouge là, comment on fait?
C'est ce bouton.
Ah, ce bouton là. Ok. Merci. Okay, and therefore I discovered some months ago, a very interesting paper of Sancerna, and therefore the other papers of Marsden Group and the book of Error and Collaborators. But preparing this lecture, I discovered this non-published paper of René de Vaugeler, who proposed to think about symplectic integrators in 1956, and of course this paper was rejected. Therefore, I will present what is classical in symplectic numerical schemes, but it was wonderfully presented yesterday too. And therefore, the idea of this paper is to switch to quadratic interpolation, and therefore all the Simpson quadrature formulas, and for to obtain the discrete Lagrange equation, the simplistic structure, but for a very, very simple numerical example. The question is to consider the action with this kind of very classical Lagrangian, and the idea of discretization is to cut this action with several time steps, and therefore you have to consider this integral of in this integral time of this Lagrangian, and therefore you have at the left of the interval QL, at the right of the interval QR. What is classical is to consider that you have a P1 interpolation, and therefore the derivative is just the finite difference between these two guys divided by the time step. And for integrating the potential, you just have to use the mean rule, the mean point formula, and therefore you have this very classical expression of the discrete Lagrangian, and after that the action is the sum of all these guys, and when you say that this action is stationary among the variation of Qj, you obtain these relations which were presented yesterday, and you obtain this kind of Euler-Lagrange, discrete Euler-Lagrange equations. And when you look to the finite differences, you see that it is a consistent discretization of the equation of motion. After that, you switch to symplectic vision, and therefore you introduce the momentum, which is just the derivative of the Lagrangian among the right variable, and therefore you obtain these two discrete moments of the times j and j plus 1, and you make some algebra, and therefore you have this system of discrete momentum equations, state and momentum equations, and you have a discretized version of the Hamilton version of your dynamical system. All this is classical, and after that you can, for a linear problem, you can, for an harmonic oscillator, you can write the numerical scheme as a transition matrix phi, and this phi transition matrix, it is a symplectic for beginners, therefore it is the scheme is symplectic, which is equivalent to the fact that the determinant of this matrix is equal to 1. And moreover, for this specific scheme, the energy is also conserved. So this scheme is very popular. And groups working on these schemes remarked that it was also the very famous scheme in solid mechanics proposed by Newmark in the late 50s. And this is in this paper of Mersden and collaborators. So I implemented this scheme with for one period of an harmonic oscillator, and you see that when you refine the mesh, you obtain a solution which is very quasi perfect and very correct. Now I switch to P2 finite elements because P1 is interesting, but P2, with P2 you begin to look to a non-trivial interpolation. What is P2? P2 is just to consider a P2 quadratic interpolation, and you introduce what we call the basis function. In black, it is a function associated to the left degree of freedom, and for the middle degree of freedom and the right, it is equal to 0. The same reversing the two objects for the phi1, and for phi1 half, you take a function which is equal to 1 at the middle and 0 at the boundaries. Therefore, you have this algebraical expression of these guys, and you can look to this popular book for numerical analysis. So you just do quadratic interpolation, which is not very complicated, but which is very interesting. Therefore, from the given values of your function, you consider this magenta curve, which is a P2 interpolation, and you have this derivative at the left in red, the derivative at the right in blue, and the derivative at the middle in black. And at the left, you see that the derivative is exactly the scheme, the upwind scheme proposed by Gear in the 70s. And in the middle, you recover the usual scheme with the P1 interpolation. So now, what is the idea? Maybe it is a new idea, I don't know. It is to switch from the computation of integral from very crude integration to much more elaborated one with the Simpson integration. And with Simpson integration, you take 1/6 of the left value, 1/6 of the right values, and 2/3 of the middle value. And therefore, you apply this job for the two terms of this integral. Therefore, for the left terms, you have to compute this combination of the square of the discrete gradients, and at the right, you have this combination of the potentials. So you have a Lagrangian, which is now discrete Lagrangian, which is now a function of the two extremities and the degree of freedom in the middle. So you begin to say that you apply this Maupertuis principle for the middle value, and you say that the variation of this section relative to Q G plus 1/2 is equal to 0. You compute a while, and at the end of the computation, you have a discrete Euler-Lagrange equation in the middle, which is consistent with the equation of motion, and you have this non-trivial expression that allows to compute the degrees of freedom at the middle compared to the degrees of freedom on the points of the intervals. You see that you have a stability condition, which is that the time step has to be reasonable compared to the dynamics of your harmonic oscillator. So now you say that you can go to the previous step, replacing your Qm in the previous expression. Therefore, you have a reduced Lagrangian, which has this expression, and I'm too old to do this by hand, and I'm using my favorite software for formal computation, which is SageMath. And when you have done that, you obtain a discrete Lagrangian, which is absolutely not trivial, just in order to approximate you obtain a discrete Lagrangian, and therefore, after looking to the variations of this Lagrangian relative to a given point, you obtain these Euler-Lagrange equations, which are absolutely not trivial. In particular, this term, you cannot invent it without doing all this stuff. Of course, it is consistent with the previous equation. A natural question is to look at the truncation error of the previous scheme. For the truncation error, you consider that you have a solution of of your differential equation, and you look to the scheme, but it is no more the scheme. You replace the value by the Taylor expansion of the solution. Therefore, the scheme is not equal to 0, and the truncation error is by definition the value you obtain doing this kind of computation. And after some formal computation, you see that the scheme is fourth order, which is a good surprise. So it is important for the application to look to the linear stability. Therefore, you look to this equation and you write this equation like a recurrence relation of degree 2. Therefore, you look to the roots of this equation, considering qg minus 1 is equal to 1, qg is equal to r, and qg plus 1 is equal to r2. You have an equation of second order, and you compute the discriminant, and you are very lucky because this discriminant is negative, and because it is negative, you have two roots which are conjugate complex, and the product of the roots is equal to 1. It is the ratio between A and C which are equal. And you see also that the stability condition you have obtained before is recovered with this analysis. For the symplectic structure, you introduce the momentum, which is the derivative of the reduced Lagrangian. Therefore, you obtain this kind of expression, which is absolutely non-trivial again. And you put this expression for these two points. You use the discrete Lagrange equation. Therefore, you obtain the discrete Hamiltonian structure with a new matrix, which is given by this expression. And the determinant of this matrix is equal to 1. Therefore, the scheme is symplectic. Okay, I used it for pendulum, but with a big initial angle in order to go to the nonlinear case, but I present only the linear case. And therefore, this is just the scaling we did. I use the same problem that previously. The previous result for Newmark are in blue. The new result for Simpson are in red. Therefore, you see there that Simpson is very better. I present the state and the momentum with 10 meshes, 20 meshes, and 40 meshes. Then you don't see anything again. But you see, looking carefully to the errors, that Newmark is still second order, and Simpson is fourth order for the momentum, and fourth order for the state. So it was only for one period, so we did the same experiment for 10 meshes. For 10 meshes with Newmark, it's not very good at the end, but with Simpson it's correct, and therefore for 20 meshes or 40 meshes, you have very good results for Newmark also, but also better result for Simpson. And if you look to the errors, you have it is second order for Newmark. It is not so much second order for Newmark. You begin to see a lot of errors that are not so small, but for Simpson it is still very reasonable. And after 10 periods, we are looking to 100 periods. For 100 periods, the error for Newmark is completely outside. So Newmark is no more efficient for this kind of discretization. And for Simpson, it is still fourth order, but the error has been multiplied by 1 order of magnitude. And it was also possible to have 1,000 of periods, and it is still second order, but the error is again multiplied by 1 order of magnitude. So, conclusion and perspective, we have developed a symplectic numerical schemes. We have tested it for the simplest problem you can think. We have observed it is conditionally stable. We have got theoretical proof of this. We have the fourth order of accuracy, and I'm very happy to have this homage to René de Vaugeler, who was, at my knowledge, the first to look to this question of symplectic numerical schemes. For the future, of course, we have we will present the nonlinear case in another conference in the end of this year, and we are looking with Juan to the adjoint version, and also to have covariant extension to multiple dimensions, and to look to the problem of Lie groups also. Okay, this is a picture with Juan. I thank you for your attention.
Now we have time for some questions.
So naturally what comes to mind is why stop at Simpson? Go to higher, even higher order quadrature rules and get even higher order schemes. Why not do that?
Of course, I have this question even in mind. Time is finished, is finite. I began this work with the beginning of this year. Therefore, the priority for us is that Juan has a good tool for his applications, but of course it is a very beautiful question. But the question, the important question I have is that I am a beginner in this field, and I'm not sure that all this work, which is quite elementary, has not, maybe it has been done elsewhere. We don't find it, but as you know, it's very difficult. So if you have references of team, you look to this question of more precise internal interpolation. Of course, it is the idea we are developing, so we will gain time. And thank you, thank you.
Another question? Only my comment, it would be interesting to work in 2 dimensions also, maybe.
Yes, yes, yes.
And in particular, the double pendulum is very interesting benchmarks because it is known as in the long term being chaotic.
Thank you, Jerry. Of course, the double pendulum, but also the, I don't know to say in English, the 2p, 2p problem, which take so we recover the questions of living on the Lie group, and so all these have naturally to be developed. Okay.